Okay, we are on. All right, so today we'll actually start diving into the first concepts behind how to actually improving performance even further by the use of superscalar architecture, and what can we do with it and how to make sure everything is still correct. But before we begin, I'm gonna go over the review of the branch prediction. As I said last week, right, I'm gonna do an example. And before I do an example, I want to kind of like go back to this recap of the two-level global predictor. And if you kind of don't remember what is a two-level global predictor, is essentially you add a global history register, which kind of store what happened in the past. That register would point to the direction predictor. That's the second level. Based on what happened to the past in the global level, you look at each of the entries that are broken down by that pattern and see what happened the last time we see this pattern. Then we'll see how it works. So here is the example program. The first program is from what we used last week, right? There's a loop and there are two if-else inside the loop. And you can see that the first condition, which is whatever is in the loop, has an impact, right, on what's going on in the if-else. Because in the beginning, if-else for the two if-else is going to be true. And there'll be one discrepancy in the middle. The first one would become false later, one cycle, one iteration later than the second one, right? So here, if you want to kind of like draw out the result of these three condition check, right? The first time the loop is true, if true, the second if true. So that's the first iteration. Here's the second iteration. Here's the third iteration. Loop is true. The first if is true. The second if becomes false. Then the third iteration, loop is still true because we are basically looping, right? And the last iteration is again true, not true, not true. Not taken, basically, not taken. Then the last iteration, not taken. At the end, because the loop, we exit the loop, so we don't take the loop, right? Our second example is simpler, one loop, one if-else. Take the loop, take the if, take the loop, take the if, take the loop, take the if. This will happen for 10 iterations, 10 pair of two TT in total. And then that would become TN for 10 more pair followed by N. Right? So that would be the pattern of the second example. So let's make this assumption. At the beginning, you have 2-bit GHR, 2-bit saturation counter. Pick one starting value. So do you want to have it start at 0001, whatever value you can pick later. Okay, so let's do the first example 1, and see what happened. So as we said earlier, this is branch.
Sorry, Professor. Can we get back to the last example? What happened? What if we not define the L? I mean we only tie the if. The branch predictor also do the same thing, right?
What do you mean by not define the else? Like if and there's no else?
Yeah,
right?
just only if.
Okay. So
yeah.
If that's the case, it's still a branch, right? Because if you think about it, here's what happened. If do something, right? This code, let's say this is line number n in your assembly. This will be line number n minus plus 1, for example. And then if you don't do that, it would have to jump from n instead of n plus 1 to be maybe to n plus 10.
Oh.
So at the end of the day, you still have the branch, right? So instead of something like this, you branch into the if and into the else block, right? In this case, it's not. It actually branched into the if, right? And then this would branch out and merge at the end because like I don't do the if. That's a great question actually, because it has some connotation in like when you have to process the program. So in terms of compiler, there are tricks you can do. And it's actually awesome that you asked this question. The whether you have the if or not having the if doesn't matter. You still create. This thing is called basic block. So you create two basic blocks regardless. The one that takes the if and the one that doesn't take the if. It can go to the else or it can just merge at the end. Right?
Okay.
Oh, here is the pattern of the first example. True, taken, right? For 2 times, then taken, not taken, then taken, not taken, not taken for 2 more times. And then not taken at the end. This is when I is 0, when I is 1, when I is 2, when I is 3, when I is 4, and that's when you exit the loop. Right? Everything is clear so far. Now, give me some initial conditions so we can proceed forward. It can be any number. So we have 2 bits for the GHR, and we have 2 bits for each of the local counter. Any number is fine as long as it's 2 bits. All right, instead of waiting, I'll just initialize everything to 0. So let's say I assume everything is initialized to 0, right? So let's go through this and see how it works. The first prediction is I'm going to look at a GHR. What is the value of my GHR? Right now, I'm trying to predict this one. I'm trying to predict what to do in the first branch, the first one. I'm trying to make a prediction for the first one. And let's say taken is 1, not taken is 0. Right? So I first look at the GHR. It's 0, 0. So I'm gonna look at the entry that are 0, 0 in this part, which is this one, right? And then I look at the saturation counter, it's 0, 0, which means I'm gonna predict 0. The saturation counter works the same way as the saturation counter with a 2-bit prediction. So in that case, it's still strongly not taken. So I'm gonna say, hey, not taken. So this is my prediction. So I'm gonna first predict not taken, right? And here's the trick. Let's do the update, and I'll start to do the update so it would be more and more clear on, hey, this is gonna make sense going forward if you run the program for a long time. So I say, hey, I predict not taken. I predict taken. Then in reality, it's not taking the branch. Oh, sorry. I predict not taken. In reality, it take the branch, right? So this is what we do. First, we update the local counter, right? This would change from strongly not taken because we take the branch. It would move to weakly not taken. So that's 0, 1. Why do we do that? First of all, it basically trying to update this information. The last time we see GHR 0 and 0, I see not taken. So I'm going to update my status to be closer toward not taken whenever the last time pattern I see GHR of 0 and 0. And now, what's the value of my GHR? Initially, it's 0 and 0, which means I initially think, hey, the last 2 branches are not taken and not taken. Now, this branch is taken, right? Because it actually does take the branch. Here, it take the branch. So that's in reality. So GHR instead of 0 and 0, so this is 0 and 0, now becomes 0 and 1. So the way I update my GHR, this becomes 0 and 1 because 0 and 0 is initial condition. You kick one of the 0 out, and then the last branch is taken, right? So you update that. The next prediction, which is for the second branch, you then look at the GHR 0, 1. So you look at the 0, 1 entry. So what's my prediction?
Not taken.
Not taken, yes. So you're going to say, hey, I'm going to predict not taken. So here's my prediction, not taken. I will update this because in reality, it takes a branch again, right? So this becomes 0, 1. What should be the value of GHR?
1, 1.
1, 1, because you take the branch twice, right? Then you go here, again, predict not taken. In reality, it's take the branch. So you update this into 0, 1. You again predict not taken. GHR is the same thing because you took the branch all the time, right? So over here, predict not taken. And you're like, ah, crap, not taken twice whenever I see 1, 1. So I'm going to update this to 1, 0. Right? So then the next time, what would be my prediction? So we are done with this. What about this one? Look here.
It will be weekly taken.
This weekly taken. So it will predict, hey, I'm going to take the branch now.
Yes.
Whoa, sorry. Can I undo that? Nope. Okay, so let me write it again. So here's the, oh God. I hit like erase all on the page. So this is the pattern. So we are at 1, 1, right? So this is 0, 1, 0. Oh. Zero, 1, 0, 0, and 1, 1. We are predicting not taken, not taken, not taken, not taken. So we are at here, we predict taken. So we are at this loop, right? So we will again predict taken, right? For this guy. This guy is correct, correct. So we are not correct here, not correct here, not correct here, not correct here, correct for this guy. And then correct again for the last one, right? So this is our, so there's 7 of them. Here's our prediction. So we here now, it's always taken. So everything update, everything's the same update, right? Do you see that it doesn't impact whatever I do in here? It just maintain that, hey, the last time I see taken and taken, I'm going to update that saturation counter that only tie to the last time I see taken and taken. So that's the, I guess that's the beauty of this approach. You only update the entry that tie to the GHR. It doesn't impact the other entry that doesn't have the same history pattern. So the GHR dictates that. And it kind of reduces collision in terms of like, hey, I'm going to update the same thing over and over again. Right? So the next time I'm here in this not taken branch, I will predict taken because I'm still at the same state, right? Then I'm going to update it this way. First of all, right? This is not taking the branch. So I'm going to say, hey, last time I see this, it's going to be 1 and 0. I becomes weekly taken. And then this will be updated to 1 and 0. Right? Because I see taken and not taken. So you look here, it will predict not taken, right? Which is wrong. So it's going to update from here 0, 0 to 0, 1, right? This would be because we are here, right? So you see not taken, taken, that's 0 and 1. So to make sure I don't hit that button that says erase all on the slide, 0 and 1. Right. So we are actually right here now, taken and not taken. So we go back to here. 0 and 1 is not taken, right? So you are correct. You're going to predict not taken. Then the way you update this, 0 and 1 goes to 1, 1. Because it is not taken branch, so I'm going to go to the more strongly not taken part of my saturation counter. It's not taken and not taken, so that's 1 and 0. So you update this becomes 1 and 0, right? And then with 1 and 0, then you look at this entry, it's 0 and 1, so you're going to predict not taken again for this loop, this 0 and 1 now get updated to 1 and 1. 0 and 0, my bad, 0 and 0. 0 is not taken. We are not taking the branch. 0 and 1 get updated 0 and 0. It's not taken, 2 is not taken in a row, so this becomes 0 and 0. You go back here and you then use, hey, it's probably not taken. Right, for this branch, we predict not taken, which is wrong, right? And then you keep going forward here. A few observations. First of all, initially this would suck. So if you start booting your machine and running program for the first time, the first probably 1,000 instructions, it would be slow. How many of you realize when you start a program, in the beginning, the program is going to be a little bit slow and it'll take like maybe 1 or 2 seconds to kind of warm things up? That happens. Well, this is one of the reasons. It's warming up the branch predictor. It's warming up the cache. It's warming up the main memory. So many things are being warmed up. Once it's warmed up, it's going to be really good. Why is that the case? If you go back to our code, right? Usually in the real program, the loop doesn't go around 5 times. It would go around hundreds, thousands or millions of times. So that's what happened. It's going to try to record the history, and most of the time the history is going to be roughly good. So your correction, once it's warmed up, is going to be really good compared to just using 2 bits, right? Using 2 bits is a little bit odd because at the end of the day, it's like, oh, okay, it's not that effective. But here you have a way to differentiate between each pattern and what do I do in the past 10 pattern. So in the real machine, GHR will be long. It can be 32 bits, 64 bits long because we do have that much room, right? In a real modern machine, you can make the GHR really long. You can make each of the local counter be more than 3 bits, and you can make the state transition more complicated. You can even do a combination of each of the techniques, right? But this is like a general overview of how you can use the GHR for your benefit. I leave the worksheet number 2 for you because if you want to fill in the worksheet later, it's totally okay. With the second example, right? You can feel free to try it out, but before I dive into like this and spend like the next 10 minutes drawing things over just for the loop that has the pattern. Taken.
Professor,
Yes.
as we have selected GHR to be 2-bit and our counter is also 2-bit, so we have four entries in this table. If we increase GHR bits, then we linearly have to increase the counter as well, bits of counter as well.
Doesn't
right?
have to, because the local counter is basically its own saturation counter. So if the GHR is 32-bit, I can still make the local counter 2 bits. It just means that now with 32-bit GHR, how many entries? So if I have a 32-bit GHR, right? 32-bit GHR, how big is the size of this table?
It's 2 power 32.
2 power to the 32, right?
Yes.
So if I make that for each of the entry in the GHR, each of them, I say, hey, it's going to be 32 bits. That table is going to be pretty huge, right? Most of the time, GHR is longer. Most of the time, the local counter is not as big. Think about it. If you have going to have a saturation counter for 32-bit long, and then state transition is only taken and not taken, how many loop or how many if else it requires to actually fully learn, right? So that actually the most of the reason behind usually you have bigger GHR and smaller local counter. In this example, it's the same size because it's 2 bits, both of them. It is like already short, right? It's more likely the GHR, it would be more beneficial if my GHR is bigger than if my local counter is bigger. It's also likely more beneficial in terms of cost because adding the GHR, I mean, actually, no. Because in terms of cost, adding 1 bit of the GHR it's 2 to the power of n. right? So that's like something that has to be kind of think about.
All right.
So how about the two-level history branch, local history predictor, right? Almost the same thing, but we don't have the GHR. No, we have the local history register that use the PC. And the thing is, the size of this, it's not going to be equal to every single possible value of the PC, right? Because let's say a PC is 32 bits, it means that if you have support for all the PC, it's going to be 2 to the 32. So the number of entries in the LHR is just limited to whatever number of entries you want, and you hash it. You hash the PC, so sometimes you have share entry for PC1 and PC10, for example, and PC12. And then another entry will be shared among the PC0, PC3, or something like that, right? So multiple program counter can share that one local history register. Then that local history register just works like a GHR, but now it's you use a PC to hash it first. So here's the same example with the same program, right? And let's assume for entry LHR. For entry LHR means that I have 2 bits for the way I identify the PC. And let's assume one more thing. Let's assume that each of these branch is unique PC that has 2 different entry. On my LHR. Basically, for each of the loop, it goes to the different entry in my LHR. That's not always true, because let's say I have 4 entry LHR and have 10 branches. Some of them would collide into the same entry, but that's fine, right? But that's fine. It's just basically they share that one history register. So the way it works is, if you look at the branch pattern, what's the pattern for the loop? I loop 5 times, right? So branch 1, this is the loop. This is the first if. This is the second if, right? So the loop is going to be taken, and not taken. The first if is going to be taken, not taken, not taken. That's I less than 2. And then taken, not taken, right? So let's assume in the beginning, I start with 0 all the way, right? Then, depending on where you are, in the beginning, the first thing you have to predict is this loop, right? So you go to, let's say this is the LHR that tied to the loop. This is the first if. And this is the second if. Right? So then there's going to be a local history register for the first loop. Is take the, so you look this to predict not taken, and it take the branch, so you update from this to 0, 1. So like, oh, hey, it should be taking. Then this is going to be updated to, again, 0, 1, right? But that's for the loop. The next branch, you're going to have to predict for the first if, right? Then you go to this one, you look at 0 and 0. Okay, LHR2, where's that table? Look here. You then predict not taken, right? This is prediction. The first one is not taken. The second one is not taken. You update it. They're going to be 0, 1. Again, this is going to be 0, 1. Then you're trying to predict for the second if. Again, not taken, because you look here, and then you, my bad, you look here and then here. So that is not taken. You update this to 0, 1. You update this to 0, 1, right? You predict not taken. So that's the first iteration. The second iteration, you now predict for this guy. So you look at the LHR for the loop. It's 0, 1. So I'm going to look here. Predict not taken. In reality, it's take the branch. So it's going to become 0, 1. This will become what? 1, 1, right? Because it's taking the branch twice already. You predict not taken. Then the next time we will look here, if you encounter the loop, and it's going to keep updating this until it becomes 1, 1. Now the difference here and the earlier just 1 GHR is now for the loop branch, you then gonna have its own pattern. Its own pattern of taken, then not taken. You have more impact into what I'm gonna predict, rather than I'm trying to take into account of branch 1 and branch 2 and branch 3 all together. But because there's limited number of LHR, it means that some of these branches would share the same entry, right? So it's still trying to capture this global information. Because in a real program, you're gonna have multiple if, else, and loop. So in that case, you're gonna have multiple branch. So PC would share single entry. So that allows you to kind of like, hey, I'm gonna add more entry. I'm trying to separate out each of the local decision. But I'm going to try to tie in the global decision because they're gonna collide in the LHR. So that's how you go through the local 2-level local branch prediction, right? All right, so that's how you handle branch prediction. The other way, so we're gonna continue on to what else can I do to handle branches? Any question?
As you said that we can have the same entry in the LHR for more than one branches. So will it not affect the prediction?
Well, it does, right? Because now you have 2 branches that update the same entry. So it means that now you are trying to assume that the 2 PC for the 2 branch has correlation. If they don't have any correlation, then it's going to be basically kind of colluding, not colluding, but like corrupting, right, the information. But hopefully we have enough entry so that at the end of the day, it still capture both branch information. So it should be good enough. And in reality, it's actually pretty good.
And is this the same process called aliasing? Because I just read that which says that an entry, a same entry in the register shares 2 or more branches share the same entry.
Mm-hmm.
I just read it in a research paper you put. So I just want to ask that aliasing is the same process. Is this
The what?
the term aliasing?
Aliasing.
Yes, aliasing.
So aliasing means that you have the. So what is an alias in computer science?
Well, but the paper, I just read this term in the paper and then I googled it, and it says when in branch prediction actually when
No, I want to ask, like, so because you have a background in computer vision, right? I think both of you have a background in image processing. So what is aliasing in image processing or signal and system?
I think mixture of 2 signals. I'm not sure about that.
All right, so let me use my other monitor and then I'll see if I can share that screen. So here is do you see my screen?
Yes.
So if you are in any form ever of image, like any signal processing, this is a 101. So I'm going to teach you something sidetrack, but it's a must for both of you because both of you do image processing. In
Yes.
signal, which is, I don't know why you'd never seen aliasing before, but it's super important. Have you ever seen an image of, like, let's say you look at the movie, right? And you look at how a car is driving. Sometimes you see the view and it doesn't seem like it's moving. right? That is because of aliasing. What actually happened is when we process information like image or audio, right? We have to do what? One of the first steps. You are trying to convert continuous signal into discrete.
Sampling.
You have to sampling. You have to do sampling, right? Aliasing means that the sampling rate is not high enough that you ended up seeing two possible signal. This is for example here. If you undersample, right? You undersampling, it is not high enough. The sampling, so look at this image, right? Look at this particular image, which I guess I have to zoom. Can I zoom in? Can you see the image?
Yes.
That'll be like dot, right? That dot are the sampling. So each dot is when you sample the signal. If you sample for enough time here, like you have so many dots, so you know, okay, that's my signal. But if you don't sample for frequent enough, this can happen. You see a dot here, you see a dot here, you see a dot here, you see a dot here. So you can draw basically two signal with the same sampling information, right? So you ended up saying, hey, which one am I going to basically which one am I going to be my final signal, right? And at the end of the day, you are likely to get this sine, like a low frequency sine curve, rather than the high frequency one, which is the true signal, right? So this is the aliasing problem. What does aliasing mean? Well, this is undersampling problem that cause aliasing. Aliasing means I can have two things that map to the same information. Two things that map to the same information, which basically means in this case, I have two signals that would map to my sample result, right? So hopefully you get two information in one go. First of all, what is aliasing? And how is that, what's the connotation in signal processing, which I hope you now, I hope it's super clear for both of you now, right?
Yes.
And let me stop sharing my desktop here. So can you see my slide now, or is it not showing? Not probably not showing up. So share here, and then I have to share my screen again here. All right, so it show up now, I think. So this is the aliasing problem in signal processing. By the way, super important, like really, really important. So one takeaway from this class, take that aliasing away. If that's like the only thing you can take away, take that first. Because it is much more important than anything we're going to teach for you guys. Because when you work on signal processing, you must know this. You must know what is aliasing. That's like a must. That's like the first, I would say the first couple of things I learned in signal processing class. So if no one ever taught you that before, they fail teaching signal processing class. They fail miserably. This is a must. I could even say they suck majorly. That's a must know. Either that or you forgot about it, which means I would say they fail without actually them failing. It's now you failing because you need to know that. It's super important. It's like you write a program and you don't know what if else is. It's that important. Aliasing is that important because it basically means that are you getting the right signal? Right? If you get the wrong signal because undersampling, whatever you're trying to do is useless. It's crap. Which means I'm a little bit disappointed that you don't know what is aliasing, first of all. But hopefully that's the main takeaway from this class. What is aliasing and what's the context in signal processing? That's super important, right? Anyway, regardless of that, aliasing in this context, it means that you have two things, two entity that maps to the same name, right? So in this case, the same name meaning the same, I guess, entry, or if you're reading the perceptron branch predictor, it might mean like the same group of entries that you're trying to do the prediction. All right. It kind of means that we don't have enough hardware to keep track of every single individual branches, so they're gonna have aliasing because they're gonna collide to the same entry. Is that clear?
Yes.
Okay, cool. All right. Good. So it's good that you ask these background questions, and these are really basic. So if you don't know these things, it's good that, and I appreciate that you look it up, right? So that's awesome. Yay. Please keep doing that, because I cannot, right? For the sake of time, I cannot cover everything that you're supposed to know outside of this class. Right? So these are basic computer science, computer engineering concepts. I will not expect you to not know what is aliasing. Yeah, if you graduate a program, you don't know what's aliasing, you fail. That's like the, so you can tell your friends that too. It's that it's used everywhere. So if you never heard about it before, good that you heard about it now, and I hope that's one of the key takeaway of this lecture. But hopefully that's not the only thing, because then I'm gonna be bummed because we're gonna talk about many things. All right. And it's good that you asked. Actually, please keep asking this. I might sound disappointed, but I'm more disappointed in the program you graduate from rather than disappointed in yourself, right? Don't feel that way. I'm just like, who the heck teach you guys signal processing? Because that's super important, and you are working on signal processing, and you somehow doesn't know what's undersampling. That's a no. That's like, I work in computer architecture, but I know enough signal processing that these are super important, right? Anyway, so please keep asking this, because this fundamental concept, I wouldn't mind teaching. It would go sidetrack for sure, but I wouldn't mind making sure you are aware, right? And I know enough about computer engineering in the breadth of like the other classes that I can feel like, okay, these are important, these are not important, and you must know certain things. And for certain other things that it's okay to not know, right? And the fact that you are here in this class actually show that you're interested in the breadth of knowledge rather than the things that you actually want to work on, which is awesome, because in the real world, you can just say, hey, I want to work in computer vision, and you're done, right? You have to know other computer engineering concepts that would make you have higher value. You know how to apply, and you know how to like use other techniques to apply it for your own projects. Anyway, so let's continue on to how else can we handle branches, right? How else can we handle branches? The first method you can do is called, it's not going, slide. Here. The first method we're gonna talk about is called branch delay slot. You will see this in the MIPS R4000 in the manual. It will talk about the branch delay slot. We are not gonna ask you to implement it, so forget about this for now. But here's the concept. Branch delay slot is during a branch instruction, right? During a branch instruction, instead of doing the prediction, one thing you can do is, well, if you know that, hey, that's a branch, right? So you have fetch, decode, execute, memory, and write back. And let's assume you have the BTB, right? You have the BTB. So when you fetch the PC, you know is that a branch or not. You know that, hey, that's a branch. It's fine, it's a branch. We would have to do something. So let's say instruction that is a branch is in the fetch, right? It means that even with data forwarding, even with data forwarding and everything, I don't know what I need, essentially, what I need to handle the branch until which one. So with data forwarding, you can forward things to decode, right? Because you can forward the register value to the decode stage. But unless that instruction B is in the decode stage, you don't know, hey, what operands do I need? What do I compare? I just know that's a branch. I don't know, is it branch if it's 0, branch if it's less than, branch if it's greater than, right? You have to wait until decode. So it means that if this is a branch and I don't want to do prediction, it means that I have to stall for 1 cycle, even with the most aggressive way of data forwarding, right? So it means that I have to stall for 1 cycle. In MIPS R4000 and the branch delay slot in general is, well, if I know I have to stall for 1 cycle, I will put an instruction that doesn't have anything to do with the branch in that cycle, right? So your question is, well, how can I detect this future instruction, right? This sounds like magic. In fact, you can use the compiler to detect. So let's say you have a branch like this, right? In the program, eventually this block would converge with if, else, right? It would converge. Once you're done with the if, once you're done with the else, for sure you have to run something in the future, right? So what you have to do is, if you have a branch here, right? You have no idea what code in the block 1 and block 2 you would have to run for sure. There's no instruction in here that guarantee you run both things. But in block number 3, if you look at this, there's a high chance that there'll be some independent instruction that has nothing to do with the branch, and you put it there. You put it there. So this is how you do it. Compile time. Then that instruction, right, for unconditional branch is easy to fill in because you know exactly where you're merging. You know exactly where's the beginning of this part, right? For conditional branch, this is harder because sometimes you don't know where the heck you're branching to, right? Are you doing this? Or are you doing this? Oh, okay. Let me re-explain this, right? So unconditional branch, what is that? Let's say you have a function call. You know you're jumping there for sure. This is unconditional, right? So you know that with block 1, you branch to block 2 is not PC plus 4, but you always go there. So there's only one path from block 1 to block 2. There's no if else. Then you are guaranteed that you can find something next nearby in block number 2. You don't have to search far in the future, right? This is conditional branch. You have block 1 merging, well, diverging into block 2 and block 3. So that's conditional. You don't know whether you're going block 2 or block 3. Then it's merging back. So when I said it's harder because you can't find it from here, you can't find it from here, you have to find it from here. Why is that harder? It's harder because it's further away. So the guarantee that you can find something independent from the code further away is smaller. It's way smaller because you might do something with all the variable. So nothing is new. Nothing is unrelated. So you can't find things to fill in. So that's why I said harder. Harder in the sense of it might be impossible to find that one instruction because the if impact every single variable, or the if impact half of them, the else impact the other half. So where the heck would be my new instruction that has nothing to do with the if or the else, because both of them would impact some of my variable, right? So that's why it's harder to find. And here's some example. So let's say you have instruction 1, 2, 3, right? And this is the branch. This will become the bubble that you have to fill in, right? It's because it's a branch. And this is instruction 4 and 5, which is like the path, like this is the branch path that you're running. What you do here is you find instruction 6 that are inside in the future to put it here. You would finish instruction 6 because it has nothing to do with your friends at all, right? It was like, okay, I finished 6, no one care. Good, yeah. And then I go ahead. And this is done through actually modifying the assembly. So the assembly code would already reflect this. You would retire things in order anyway. It's just 1, 2, 3, 6, 4, 5, right? And move 6 up in assembly code. So if you compile and look at the assembly code, it actually will get moved up in the assembly. So the programmer already knows this. The programmer knows the shift up because of the branch delay slot. You can have the fancier version of this too. It's called, one thing you can do is called squashing. Squashing is if branch fall through. Basically you have a branch, it fall into the branch. You don't have to execute the delay slot. So this will be like both a mix of the hardware and software approach, right? So you have a normal, so this is a normal instruction like this. This is with delay slot. You have branch X, right? And sometimes you can't find anything to fill in. So you fill in with bubble. This is bubble because you cannot find whatever you want to put in here. It's just, hey, I cannot find the future instruction to put in my delay slot. So I put in no op, which is bad because you stall, right? So in that case, you can do delay slot plus squashing, which means that I'm going to fill instruction A here. Because branch X, what does branch X do? Branch X go back to X, which is going back to instruction A, right? Then, because you know that if you fall through the branch, you have to run instruction A. So you put A in there, in the delay slot. In that way, you don't have, when you branch it back, you don't have to do instruction A again because it's already in the delay slot, right? So that's another optimization you can do. All right. So basically, the goal here is, hey, what can we fill in? Can we guarantee that this thing would have to be run? If we can guarantee that, in this case, we do squashing, put instruction A in the delay slot. Right? So what else can we do? So that's with the branch delay slot. Not many processors use it now because you can do branch prediction really, really well, or you can do this option, do something else. That something else is called, one of the techniques called fine-grained multithreading. So hardware will maintain multiple program counters. How many of you heard about Intel hyperthreading? Or AMD has its own version of hyperthreading too. If you buy chip, you will say, hey, we have hyperthreading technology. What it means is, instead of maintaining one program counter per CPU, you have 2 program counter and 2 register files, like 2 copies per CPU. Both of them run 2 threads in your runtime, run 2 threads. In reality, you basically fetch 1 thread. But if one of the threads happen to stall, you switch right away and fetch the other thread. Basically, it means that I have another program counter ready to be fetched whenever I have to stall my pipeline. That's simultaneous multithreading. Fine-grained multithreading is like a put in steroid for that. I will have so many program counter so that every single cycle I can fetch another thread. Has multiple threads. Each cycle you fetch a brand new thread, brand new program counter. In that way, you don't have to care about the branch because, well, I will know by the time I have the condition checked. What do you do? What do you do with the next PC? Because I was running the other thread. So that's fine-grained multithreading. We'll go into more detail when we cover the GPU. GPU use 2 main techniques to get that throughput. Fine-grained multithreading and single instruction, multiple data. So those are the 2 main things that GPUs give you. That's the main architectural concept behind its throughput. Also, main architectural concept behind, sometimes if you run single thread on GPU, you cry that it sucks. because of that reason. We will have a long discussion on the GPU. We have lecture for that toward the end of this class, this course, this semester. Again, the downside, as I said, if you run single thread on the GPU, it would be really slow. And you need extra logic. It doesn't come freely. So you need actually to maintain those multiple copies of the program counter, multiple copies of the register. If you look at the size of the register files on a GPU, for example, you might be surprised. It's hundreds of kilobytes. Hundreds of kilobytes. That's big. Compared to CPU, you have 32 entries. Each entry is 64 bits. How many is that? Well, 1 kilobyte, right? So the size is so different. So you need extra logic to keep maintaining those contexts. In this case, with fine-grained multithreading, we'll go into more details when we have to talk about multithreading and the GPU, but we can use it to correlate both control, which is branches, and data dependency, all the data forwarding you don't have to do. Because you're running another thread, you can wait until everything is written back. So this is kind of like the main basis with modern GPU, and it's kind of an old, actually it's super old idea in CDC 66000 by Thornton. There's a paper at AFIPS in 1964, and then it explained the architecture behind the CDC 66000. So that's one of the proposals that, hey, let's use this technique. Another machine is called Denocore HEP, another machine that use MIMD computer, multiple instruction, multiple data computer. So these are kind of like the basis behind the GPU. If someone tell you, hey, GPU is like innovative, it's a totally brand new idea, the way people build GPU, these are old ideas. Most processors, the way we work on building new chips, we build on old ideas. Fundamental concept doesn't change a lot, but it's the way we engineer. The GPU is awesome because they engineer it perfectly for the application they have to run, right? I play games. I love gaming. And I love buying and looking at GPU specs because, well, it does give me cool graphics that I can play with, right? So it's a really great way to engineer old idea to make it make it new and useful, right? These ideas were actually used for high performance computing application before this, right? It's useful in the context back in the day, and now it's kind of shift into the different application. And now shift into like new, a lot of deep learning application, a lot of machine learning application, right? So the thing, as we said in lecture 1, you need to know the user's demand. So we build hardware for that. That's our job. So what else can we do? We can get rid of control flow. This is also another thing GPU do, including ARM processor. And nowadays actually pretty common. I believe there's like a version of this in Intel ISA, like 86 ISA as well. I'm 99% sure about that, I think. I haven't checked. So if I'm incorrect, I'm sorry about that, but I'm 99% sure it's also there. We can do predicate execution. What does predicate execution mean? If I don't want to convert the control dependence, I don't want to do branch prediction. One thing I can do that are also pretty prevalent in ARM ISA is I would use the conditional register, right? I would use the conditional register. This conditional register, it checks what happened to my previous instruction. If an add results in a 0, if the subtract results in a 0, if an add results in greater than 0, for example, if it results in overflow, you add 2 numbers and it overflow into the 33rd bits, hey, overflow flag would be on. In ARM ISA, you can say, if that's true, run this instruction, otherwise don't do it. So that's what predicated instruction is. You execute the instruction based on what happened to the previous instruction. So there's no branch, basically. You either run or not run, but there's no branch, right? It turns into data dependency. You turn control flow into data dependency. And here's some, individual instruction is only executed, right? Only executed if the condition stored in the register match the ISA definition. If it's 0, I run. If it's not, don't run. So you don't, in turn, it means that you don't have a branch, right? You either run or just forget about that instruction. Let's run the next instruction. And here's the benefit. It gets rid of all the hard to predict branches. You don't have to do prediction, right? This means that instead of having a code block that branch into block 1 and block 2 and block 3 like this, right? Your code become a huge block 1, and if this true, you either run or not run this, but it's one block. This means I can do a lot of things in compiler. So when you do predicate execution, you can be fancy when you compile the code, and hopefully your code is faster. Because by default, the compiler know that whatever happened to that, well, it depends on the condition, but I don't care. It's a big basic block, so I can optimize assembly inside the same basic block better. The downside, if the branch is not true, right, then you have to throw it away because you have that instruction in the pipeline. It's not true, so you should not commit, throw that instruction away. So you can waste that work. You waste the work, and it requires additional ISA support. Any question before we take a break and transition into the next topic?
What I understand from predicated prediction is that you said that the code will be all there, like the if statement code as well, the else, and the compiler will decide what to run and what not to run.
Yeah. So
Right.
let's say you have the add, right? Add something, and then you do this. Add if the previous instruction is 0. It means that you either run line number 1 and line number 2. If number 1 result in the 0 flag become true, line number 2 would get run. Otherwise, you go line number 1 and then get rid of line number 2 and then run line number 3. 2 will be in the pipeline until you figure out, hey, is that a 0? Then once it's a 0, you keep 2. If it's not, you throw it away. But if your branch is easy to predict, you can use a compiler to add this, and more than half it will be correct. So you don't have wasted work and you don't have control flow, right? So there's no need to do branch prediction at all. You eliminate the branch. So that's the benefit.
All right.
Yeah. Okay. So let's take let's do 10 minutes break. We will be back at 10:10. If you have any more questions, we can come back through the Q&A after the break as well. Is that okay?
Yes.
All right, awesome. So let's see you guys in 10 minutes then. I'll go double check if x86 has a predicate execution support. And I'll be right back to check. All right, let's continue the lecture. Oops. So now that we talk branch prediction, I would continue on to the concept of to be honest, superscalar architecture and how to make your computer faster, right? But that comes with another headache called precise exception. So let's go back to the multi-cycle execution lecture. And one of the issue with multiple, like running the running things throughout the pipeline with different number of cycles is that, let's say you have add and multiply. Multiply obviously would take more time than one add, right? Because if you break down the multiply is add and shift, you do a lot of steps, right? And at the end of the day, you still need to maintain that sequential order. The instruction has to be processed by instruction n plus 1, n plus 2, n plus 3, n plus 4, n plus 5. So let's say add finished. Instruction 1 is a multiply. Instruction 2 is an add. In this case, add can finish before the multiply, just by the nature of adding, right? But you have to retire whenever I said retire, mean I finish the write back in this order. 1, then 2. Because you need sequential instruction processing. Why do you need that? So that we don't give surprise to the programmer. Surprise! I run this assembly code, then the next 2, and then back to the third one. Because as a programmer, that can be super confusing. Like, what the heck is going on? How can I debug my own code in that case, right? So our ISA requires what we call sequential semantic. Sequential semantic. Von Neumann again, right? Line n plus 1, n plus 2, n plus 3. That's simple, and it actually makes sense for the programmer. So if we revisit superscalar architecture, right? The idea is, well, first of all, we want to have in-order instruction retiring. I want to make sure I maintain my sequential semantic. Instruction n plus 1, n plus 2. N happen before n plus 1. N plus 1 happens before n plus 2, and so on and so forth. But if my previous instruction stall, superscalar said, hey, I still want to fetch the next one. Why is that the case? Why is that the case? Let's say I have an adder and multiplier, right? So this is in my ALU. It means that while I'm running an add, my multiplier is not doing anything. Why don't I fetch the next instruction and process my multiply, right? So you can execute more than one instruction at a time. You keep fetching, right? So we can keep doing this as long as we have this property. As long as we have in order instruction retires, we are okay. We can keep fetching whatever, right? And keep running things in parallel. This is a good thing. It's good for performance. We're gonna keep fetching so that one cycle, potentially you can finish 2 instruction, 4 instruction, right? This means that inside our pipeline, things can be happening out of order in any order based on whatever is finishing. We just need to make sure the write back happen in order. So we all on the same page here. Write back has to be finishing in order. The rest of my pipeline can be done in any order. So this is a superscalar architecture. You have the write back, right? And for sure, this has to be in order. You have memory, you have execute, you have decode, you have the fetch unit, right? So let's say I have a multiply in decode. And then in the execute, I don't want to do only one instruction. Let's say I want to have 2 adder, 2 multipliers, right? This means I can send the multiply to this one, right? Which also means I have 3 more things to do because I have more hardware and I have extra transistor. Why not adding? What does it mean? It means that if this multiplier is doing its thing, I will try to fetch more, right? So the add comes in here. Another add can come in here. Another multiply, I can have it comes in here. So that I can assign this adder something to do, right? And then they would finish. And it just have to make sure this is done in, oops, I cannot write, in order, right? As long as you retire, do the write back in the same order as you fetch, you're good, right? What else do we need here? We have more ALUs. We now have to make sure we have a way to store these instructions. Some of them might not be running yet. It's still waiting because I don't have the ALU to run it. I don't have the operand because it's being done right now. So this area is kind of like a staging area for the instruction. We call this instruction window. So you fetch. You keep filling in new instruction into your instruction window. The first one can be add something, multiply something, add, and then let's say this add become available first. You launch them, say, hey, I want to do this out of order. As long as my write back is done in order, I'm good, right? So I've launched the second add, then I launched the first multiply, then I launch the second add here, and then I launch the second multiply. So the order, instead of multiply, add, multiply, which is the in order instruction processing, you start running add, multiply, which is out of order. Over here, you just need to make sure you retires in the multiply, right? Add, multiply. So it has to be the same order as what you see here. As long as you're doing that, it's good. Programmer doesn't get confused. And in the hardware, as long as everything's still correct, we're good. We get better throughput because if you have to wait, say 5 cycles here, it's 5 cycles wasted. So why don't you send in the add to the pipeline? Because you can, right? So that's our idea. Superscalar architecture, add more ALU. You have multiple add, multiple multiply, multiple operate AL, like units to operate on, multiple ports to your memory. Then you have this instruction windows where you're going to keep fetching and see, okay, can I run this? Can I run this? Can I run this? Can I run this? Whenever I can run, I fire them off, right? Say, hey, go run. In write back, reorder that so that it becomes in order. To make sure the programmer is like, what the heck is going on with my assembly? I run this line and skip to the next 5 line. I need to see line 1, 2, 3, 4, 5 finishing. Right? It all seems good. As long as we can keep this order, it all seems good until we have these 2 things. Right? Without exception or interrupts, your program is guaranteed to run and finish. With exception, what is an exception?
Divide by 0 and
exactly like divide by 0. It's like it's something that you're running and your program is like, I don't know what to do with that. You have divide by 0. The program is like, how do I divide by 0? Mathematically, it's infinite. How do I represent infinite, right? So it depends on how you want to deal with it. Exception is internal to the program. It happens because of the program. And it's handled when you detect this by the process itself. You run a program, it run into an exception, you yell at you, hey, exception, could handle this. And the priority is based on the process priority, right? So exception happen depending on how important the program is. If it's like a printing job, the OS might choose to handle that way later. Like, okay, fine, if you print it later, that's fine. Interrupts. What is interrupt? Interrupts are external to the running thread, like when you hit something on your keyboard, move the mouse, have a signal input coming from your sensor. These are interrupts. You have external thing coming in that involve with your running thread. It's handled when convenient by the OS. OS will say, oh, I have an interrupt. Who are listening to this, go handle that. And the priority of the interrupts is varied. It is varied based on the importance of those signal, right? So when you have to ensure what we call precise exception or precise interrupt, it means that whenever I have an interrupt, let's say I have an interrupt here, fetch, decode, execute, memory, and write back, right? Let's say these things cause an interrupt. The instruction in the execute stage cause an interrupt. What does it mean? It means that from the programmer point of view, anything that happened before that thing in execute has to finish because that's supposed to finish. So things in here should finish, right? Then everything before this should be thrown away because it should not happen. It should not even being run, right? Because the instruction that say, hey, I'm going to do by something by 0, yay, and it caused interrupt. Anything before that instruction should finish from the programmer point of view. Why is that important? Because I need to debug what happened before that line. I need to figure out what happened exactly before that line. So you need to retire that. Because the von Neumann ISA, anything that use von Neumann ISA, assume this. It helps software debugging because you know, okay, this happened, so this caused my interrupt. It's also allow for easy recovery because you know exactly, okay, that program counter caused an interrupt. I can rerun again and resume whenever the interrupt is handled, right? An easy to restart process because you know when and how to resume, exactly when and how. But think about superscalar architecture. So these I assume in order for everything, right? But what if you have superscalar architecture, but you have out of order instruction processing? Fun, right? Because if you have a multiply and then add and then multiply and then add, let's say interrupt happen right here, right? Which means that it's supposed to finish the multiply or like raise the interrupt for the multiply. Nothing else should happen. Somehow the add and multiply and add are in the pipeline. So how can I tell which one to throw away and which one to keep, right? Because things are not in order in my pipeline anymore. Let's say this take 10 cycle, this take 5 cycle, this take 10 cycle again, this 5 cycle, right? By the time interrupt happens, it might be the 6th cycle. So my add already finished. Like, hey, I'm here, I have results, right? Multiply, raise, and interrupt. Okay, what the heck, right? So one naive idea is, well, if each instruction takes the different amount of time and multiply take 10, add take 5, add can somehow finish before multiply, one thing I can do, make everything take the same amount of time. Add 10 cycle, multiply 10 cycle, because it goes into your pipeline at the same rate. So the multiply would be ahead of the add for sure, right? The add won't come out of the execute stage after the 10 cycle. Not before the 10th cycle. It has to guarantee after the 10th cycle, add comes out. Is that a bad idea? It's a bad idea because why are you even slowing things down just because you want to handle interrupts? Well, the goal is good. You need to be able to handle the interrupts. There are techniques that we use to handle, which is basically let's make every single operation take the same amount of time. It's kind of inefficient, right? Because the downside is slow. It's so slow. So the issue, again, recap, right? Different instruction take a different amount of time, and you still need to maintain the sequential semantics, right? You need to still maintain the sequential semantics. How do we do that? So now we can start to transition into techniques that we can use to maintain sequential state. What are those? You start with the first thing called reorder buffer, which basically, as the name suggests, is a buffer that allows you to reorder things based on the instruction sequences at the end. Then we are going to introduce newer and newer idea. The next one is called the history buffer. Then the future file. And then we kind of wrap it up with checkpointing, right? So this is going to be somewhat confusing topic. So I want to make sure you kind of like have a fresh start, a fresh brain. So we'll kind of do a quick recap and we'll pause, do a break quickly, and we will resume. All right. So the first thing is pipelining recap, right? We all know pipelining. We all are friends with pipelining. You can have instruction n here, n minus 1 here, n minus 2 here, n plus 1 here, and n plus 2 here. This cause an interrupt. This has to finish. This has to be throwaway. If this is what you run, instruction n right here, n plus 1 right here because of out of order thing, instruction processing, and this is instruction n minus 1, instruction n minus 2 is right here because it's slow, and n plus 2 here, interrupt happen here. You need to keep this, throw away these, right? So let's now go into each one of this, starting with the reorder buffer. We will do a pause here. Let's do a 10 minutes go get coffee. This is the new concept completely. It can be confusing. Think about the interrupt exception. We'll resume at 10:40. Is that okay?
Yes.
Okay. So I do have to think there's like a something that's happening at TGGS from the staff point of view. I might have to attend that for like 5 minutes. I'll be right back as soon as possible. Definitely before 10:40. Is that okay?
Yes.
All right. So let's take a break. We will resume at 10:40. Okay. All right. As per all the Thai government related things, everything is delayed. So I guess nothing happened on the staff side. So basically, these are the interview by the kind of like as an agency that checks and try to like give make sure everything is in high quality, high standard. So we do interviews among like all the staff, all the professors, and likely some of you might get like randomly picked to ask for the interview and things like that, right? But what I'm surprised, like, well, you guys and are an entity that wants standard. You're asking for an interview. Why don't you have another hour set aside for people who have class conflict? Like, what's up with that? You're asking me to be interviewed, but then you don't even care that I'm actually teaching, and you're trying to maintain standard for education. Like, what the heck? Right? I could have used like a worse word, but yeah. Anyway, so let's resume our topic, and also they couldn't even keep track of like the time. What the heck is that? Like everyone need to respect everyone else's time as well, right? This is like professionalism 101. So I hope we as a human being gets better at that. Anyway, let's continue on for the topic of precise exception, because essentially at the end of the day, we want to make sure that we maintain that precise exception. The word precise means right at the exception happen, we need to know what exactly the sequence of things that happen. It should be in order, and we should maintain that. So the first structure that we're going to introduce is called reorder buffer. A buffer is used to store things. Reorder means we are reordering, so that we use this buffer to make sure everything becomes in order, right? So it's just as simple as that. So here's the idea. You can add a buffer, right? And the buffer allows the instruction it would allow inside the pipeline. Let's say you have 30 stages pipeline. Everything can be done in any order, out of order if you find, right? As long as at the end of the write back, we have a way to reorder. So we are adding this buffer to reordering things. How do we do this? During the decode phase. At decode, that's when you know the instruction coming in, right? At the decode state, you add this thing called reorder buffer. When instruction coming in, right? You then reserve an entry. So if we do this in the decode, what does it give you? It gives you in order sequence, right, of instruction that comes in. So the instruction stream that come in would be in order. So if you allocate this stream in order, your reorder buffer is already sorted. Because instruction n, let's say instruction is allocated, instruction n plus 1, which is the next instruction that you're fetching in the decode stage, will be in the next entry, right? So if you look at this ordering, it's already sorted. And that's all, right? That's all. That's how you can make sure that at the end of the day, at write back, we have a way to sort things back. How do we do this? First, you reserve the entry. So our first assumption within this entry, within the reorder buffer, everything is sorted. The next thing is, well, you have to figure out when I finish one instruction, where is that entry in my reorder buffer, right? Where's my entry? So I know that, okay, I finished the one in the 5th entry. I finished the one in the oldest entry, which means I can actually retire that instruction. If it's a 5th entry, then I have to wait until the 1st, 2nd, 3rd, and 4th finish, right? So the way you can do this will give everyone a tag. What is a tag? Anyone here know of the terminology dog tag in like in war? Or if you watch like a war movie, right? Every soldier will have a tag on their neck, like in the necklace. There'll be a tag with the name. So that's called a dog tag, right? So that's for a war, so that if sad things happen and the soldier pass away, you can look at the tag and know who passed away, right? We use this concept of a tag everywhere, including in architecture, which is we give everyone a tag, give them a name, right? My name is Rashada, Opad, your name is Opad, and then Muhammad, your name is Muhammad, right? So we give everyone a name so that when we go back to the reorder buffer, we allocate this entry, we put the name in as well. Oh, that's Opad's entry, that's my entry, that's Muhammad's entry. So when we finish, it's like, oh, where's my entry? Oh, I'm in the third entry in the list. So I'm gonna stay here and wait until the first and the second guy finish. So if you pass around the tag and you have the tag assigned, you're good, right? You're good. So when the result complete, you write the results in the reorder buffer, right? Why is this good? It just basically means that I know my result. So if someone else need my result, here you go. It also keeps track of I finished. I have not retired, but if someone else need my data, here you go. Right? So it allows the future instruction to take that data and run. So that's one benefit. If the oldest instruction in the ROB complete without exception, kick that guy out because that guy is done, right? So you write the result in the register file, that instruction finish, kick it out, right? So you can retire that way. The oldest guy finished, write that to the register file, kick the entry out so that you can keep retiring things in order. And this is where the result becomes visible. Why? That's when I write the result to the register file. Unless we finish, unless we kick that entry out of the reorder buffer, we don't write into the register file. So the programmer, when they look at the register file, it's still correct and it's still updated in order. This ensure the register file gets updated in order, right? In order of what you seen in the reorder buffer. So now we are good because if exception happen and you want to see what happened in the register file, because that was the programmer see. Programmer see a couple of things. Program counter, right? Register file. So you know already in the pipeline stages, if exception happened, what happened to the register file? And what happened to the program counter? You retire the rest in your reorder buffer that are before that exception causing instruction. And you throw it. So you maintain the rest because if you handle that exception and resume your execution, you have everything intact in the reorder buffer. You don't even have to, well, when you resume, you know exactly how and where, right? So this gives you ability to resume quickly, handle exception in the in order way, and ability for the programmer to debug, right? So this is good. And let's say you have like 5 exceptions back to back, you can still use the same technique, right? Reorder buffer will first trigger the first exception, you resume, it trigger the second exception, you resume, you trigger the third exception, you resume. And this can happen. I mean, the program that's like in the beta testing or alpha testing, sometimes you have a lot of bugs, right? You're trying to weed out those bugs. So sometimes this is required. So we are giving the programmer ability to actually debug, right? While the CPU is really fast because I do things out of order. I don't care. Programmer doesn't see this. I'm doing things in the background. No one cares. So I want to make sure these are fast, right? So what goes into the entry of the reorder buffer, right? So your next question is like, okay, I know why we need it. I know roughly in the high level how we do this. Now let's go into the detail. What do we put in there? How can we make it useful? Obviously, you need, the first thing is called a valid bit. Valid bit just tell you, can I look at this entry, or is this entry just junk, right? So if the entry is not used in hardware, it's not like that thing would disappear because you implement things in the hardware. The hardware exists, right? So you need one bit to tell, is that junk or is that a valid data? If it's one, it means the data is valid. You can take a look at that. If the valid bit is 0, don't look at this. It's just junk data. I haven't initialized it. The reorder buffer has to do with what register I'm going to write over, right? Because at the end of the day, when you finish an instruction, you have to write the result back to the register file. So you need two things. What value I'm writing and what register am I writing? Am I writing to R0, R7, or R6, right? You need to store where am I supposed to writing back? And what's the value of my add, right? Because I haven't written back that result yet in the register file. You have to store them somewhere, and here's where you store it. What else? Now, this has to do with register. That's one more thing that the programmer sees. Right? So if it's a memory-related instruction where you have to store the result back to DRAM, you keep the address and you keep the value so that you can store it back. Simple, right? Really simple. Instruction type, why do we need this? Just in case you know who has been using add and who have been using multiply, because you need to keep track of how many add and multiply are there that are available, right? Also, because we keep these two things, this is compute, this is memory, right? It's so important that you have to tell, is this compute or memory? Because if it's compute, use the register ID and register value. If it's memory, don't use the register ID because that's junk. Use the store address and store value. So that's important. Why do we need to keep the instruction type? Alternative structure, you can have each queue for memory, another queue for compute. In the next two lectures, we'll talk about a separate structure that kind of handle memory instruction called load store queue. But for now, let's assume everything's kind of there. Right. Here
Professor,
is the
you also talked about tag. We assign a tag to actually locate where is the instruction in the reorder buffer. So
right.
is
So
this tag
yes.
placed?
So here's the deal, right? You need to be able to tag the entry. We're gonna talk about how we do that in a few slides.
Right, all right.
Yeah. So when you put everything together, so let's for now assume that we need the tag, which is a good thing. We need a tag. There'll be another trick to kind of like how to minimize the tag, right? But let's for now keep the tag.
All right.
All right, cool. So here is the structure: valid bit, register ID, and register value, right? And then address if we need one, and then value for the store, right? You can kind of optimize this further because it's either compute or memory. It's not like one instruction combine two things, so you can kind of combine these two entry if you want, right? You just say, hey, it's a load or store, or it's a compute. So that's one more bit. It's like load store. So instruction type essentially. So that's a reorder buffer. So with an reorder buffer plus data forwarding, like recall our data forwarding lecture, now my data can come from three options: traditional register file, traditional forward path, this is from data forwarding, and the reorder buffer, right? Because I have instruction finish, it's not in the pipeline, it's in the reorder buffer, it's not in the register because it's not the oldest instruction. So how can we tell which data should I use, right? So when you have reorder buffer access, this is the correct sequence of what to check first. First, you check the register file, obviously. Then if the register file is valid, it means that no one else in the pipeline is updating that register. So now you add the valid bit in the register file. When that is 1, mean use this data because no one else in the pipeline is modifying it. Use the register file value. If not valid, you then store the ID, right? This is when the tag comes in. Instead of storing the value, if it's not valid, you store the entry because in the reorder buffer, you know that's the zeroth entry, the first entry, the second entry. You store the entry number of the instruction that generate result for that register. So let's say that entry is number 3. Let's say that is number 3. You store number 3. That's the ID. So you can have either a valid bit of 1 and the value go in here, or a valid bit of 0 and the ID go in here, right? So that is going to be the entry in the reorder buffer where I can find my value. Then you access the reorder buffer. Then then you check the valid bit again, right? If the valid bit is 1, it means what? You can use this value, right? You can use this value. If the valid bit is 0, what does it mean? It means I have this instruction in the pipeline, right? Because I have allocated that instruction. It's not valid yet. Whatever you see here is junk because we are computing that inside the pipeline. That instruction has not finished. So check the forward path in the pipeline. So that's when you can tell everywhere, right? Okay, where's my data? Is it in the pipeline? Is it in the reorder buffer, or is that in my register file? So this register ID kind of maps the correct corresponding entry in the reorder buffer that will write. It will write to the register file. So that's convenient. You have the connection between register file and reorder buffer. So when you have a reorder buffer access, assume these are the instructions. Right? Let's assume these are instructions. You store these information in the reorder buffer, right? And here is a register file. So let's say initially this 1, 2, 3, 4. Actually, let's make it even simpler. These are These are the instruction. These are going to be your reorder buffer, right? And this is initially the value is 0, 1, 2, 3, 4, 5, 6, 7. The reason why I erase everything, I just want to make sure the value is the same as register ID for the sake of like making it simple. The first instruction, I will say, hey, I have an add, right? What does it write to? R3, right? I add something to R3. So I say, hey, this is register ID, that value is 3. And I'm doing an add, right? So I don't know what it is yet. It is the valid bit. It's not valid. It's still in the pipeline. I'm doing that add. Then you take in the R1 and R2 here to the pipeline. Right? So you're doing basically 1 plus 2. Let's use a different color to annotate that when this is finished, right? When this is finished, this becomes 3. So I'm going to update this, right? I'm going to erase this X because it's not valid. Now it's become the value 3. I'm going to erase the valid bit here. This becomes 3. And then initially, when this instruction is in the pipeline, right? R3 should be invalid. Now you write 3 back and say this is valid. You can use it. But because the next instruction need R3, so when originally, right, this becomes invalid, and this is entry number 0, entry number 1, entry number 2, entry number 3. It should be 0 and 0. This is not valid. And then go check ROB entry 0 for the first instruction. Now you fire off the second instruction, which is this one, right? You say, hey, I need R3. I go look here, R3 not valid. Where should I look next?
Zeroth where
The
how
order
far
buffer.
of it? Yeah.
It's not valid because I haven't finished my add. So where do I look next? Data forwarding, right? Because it's in my ALU, so I can take it from the ALU. I know R3. What is R3 in the ALU? 3. It's 1 plus 2, right? So then you say, hey, I know it's 3. I take it from the forward path. It's not from the register file. It's not from the reorder buffer, but I can fire it off because I have that data in the ALU. So I would say I'm going to use a different color. So let's do orange, right? Add, what's the result ID? 3 again, right? I'm going to add to register 3. I don't know the value of that yet. It's not valid because I'm doing the add right now, but I know from the forward path that this R3 is 3. So I can fire off. I can start running this. I'm going to update R3. Go here, right? Update it. Valid bit stays the same. It's not valid. The entry change from 0 to what?
1.
1, right? 1. So now if someone else need R3, then you, instead of looking here, now you will look here because that's the most updated version of R3. If it's not valid, then you go look at the pipeline and see where's the ALU that produced R3. Once I have that, I can forward it. All right. So you can use this as a structure to enabling reorder buffer. And once this valid bit becomes 1, you can get rid of this. This becomes the oldest, right? Then when you get rid of this, you check, right? Check over here. I want to update R3. I look at the register file. It's not valid. Who owns this most updated version? Is it my entry or is it another people's entry? Is it my entry? It's not because I'm finishing entry 0. The person who owns this is entry number 1. So I don't have to update because this is not the most recent version of my data. It's still invalid. So look at entry number 1. So I don't have to update the register file, right? So everything here follows logically. It just has to follow the steps, right? One thing I love to say about the hardware is you have to kind of like do a sequence of simple steps to reach the goal. And this is one example of that. It seems complicated, but it's a series of simple steps. Your data eventually will be somewhere in the pipeline and you can find that. You just have to follow the trail, right? And you'll see where the data is.
So
Now here
actually,
comes the problem.
register files are
Yes.
acting as a pointer to reorder buffer, and finally after the write back, they will obviously occupy the result, right?
What do you say?
Actually, during the execution, the register file just acts as a pointers, we can say, to the reorder buffer, or what you said.
Yeah,
Tag.
it contains the ID, right, of that entry.
Yes, and after the write back, it will then contain the actual data, the resultant data.
Eventually it will get updated with the actual data, right? So here's the issue. Here's the problem. Problem with reorder buffer. So with the following code, right? We have multiple versions of R3. Sometimes we use it, sometimes we actually you're not using it, but we generate it. Each version of this R3 should have its own name because this is R3 version 1. We use R3 version 1. This is R3 version 2, right? Is this the second version of R3? Then we use R3 version 2, and then this generate another version, R3 version 3. It seems fine if we do everything in order, but in reality, if we do internally in the pipeline different order, how can you tell the R3 in the pipeline, right? In the pipeline, which version is that? Because we do things out of order, it means that sometimes you might see version 1, sometimes it's version 2. If version 2 is faster, you see version 2 first, right? So you need a way to tell. You need a way to tell. And the current method doesn't give you that way to tell. So the next technique is called register renaming. And this is getting rid of right after right. You see, right. So now you see this weird data hazard. You have right and then right and then right. So the order, if you do everything in order, it's like write 1 and write 2 and then write 3. But because we do internally things out of order, you can have write number 2 finish before write number 1 and then write number 3. Right? So we need the correct version of my data. That's the key message. So to eliminate this, write after read and write after write, these are not true dependency, because if you write things in order, if you finish the pipeline in order, things are perfect. But in an out of order processor, you don't have enough register file to store each version. Right? I cannot store each version of my pipeline. So what do? I then have another structure to rename my register. So this is what we did. I showed it earlier with an example. This process is called register renaming. Register ID, you saw what I did, right? Earlier, when it's not valid, I put the ROB ID in there. This is, if you go back here, this process, right? This process is called renaming. I rename what should go into my physical register. Say, hey, I don't have the data. Go look at the reorder buffer entry that is the most updated version of the data. So that would eliminate the write after read and write after write through register renaming. So the register ID becomes the ROB entry ID. That's where the tags come in. Instead of actually assigning another space for the tag, you know, hey, that's the first entry, that's the second entry. Why need extra space for that? Use the entry ID, right? So that hopefully answered the question of what about the tag. Then the register, we call this architectural register, the one that is programmer visible, right? Programmer visible. We use the actual physical ID inside the register file. So this is the same. We have the architecture register and we have the register renaming. And here's one example. So let me show the example, right? This is the instruction, full instruction. And then this is the reorder buffer. I want to just name the tag 0, 1. It's just the ID of my reorder buffer, right? 0, 1, 2, 3, and 4. Initially, let's assume this is the value, right? 0, 1, 2, 3, 4, 5, 6, 7. And one thing I'm going to do, I'm going to change the tag from number to A, B, C, D, and E. This is just to reduce confusion. In reality, these are numbers, but I want to minimize confusion, right? Again, let's go through this example and see what's going on, right? So here is what's going on. Let's change the color first. Instruction 1, right? You go and put that in the reorder buffer. We are not finished, not valid. The value is unknown. What is the source 1 and source 2? R1 and R2. How do I figure out what's R1 and R2? I then go look at the value of R1 and R2 here. In this case, what's the value of R1 and R2?
1 and 2.
1 and 2. I then fetch the next instruction. Again, not valid, right? Oh, I forgot to do one more thing. At the end, right, I'm writing to R3 over here. I'm writing result to R3. So I will have to, again, update here, right? Change it to what? Who is updating R3 right now?
Tag A.
Tag A, right? Now let's go through, oops, not eraser. I don't want to make that mistake again. Tag B, so that's the second instruction. What is the valid bit? It's not valid. I don't know the value yet, so let's put that Y. I don't know. Source 1, what is source 1?
R3.
R3. So I look at R3 in the architectural register file. What is R3?
It's tag A.
A,
What is source number 2?
R5.
5,
Right? Then I update R6 in the register file. Eraser here. What should I put in here? Right. So let me use a different color to make sure we have steps going on. Right. The add. What do I add it with? So it's not valid. C. Right. You are adding R4 and R7. So what is R4? 4. What is R7? 7. What do I write it over? R3 again, right? We are writing over R3. So we go and update here with C, because now C has the most updated version. And because we already allocate the entry for A and B, right? A and B. Remember, originally R3 is A, right? I already said, hey, for B, source 1 is A. Now I already keep track of that. So it's safe for me to change this and update this to C. Because my reorder buffer already have the source for B. So I know, hey, that's a version of R3 that I want, right? So this allows you to kind of rename the combination of this and this, right? You rename the register name. So let's go to the last instruction. I'm going to do R3 plus R2 and write over R3 again. So many R3s. So I'll say, hey, it's not valid. Oops, sorry. Hey, it's not valid. W for the value. What is source 1?
C. Tag C.
C, right? What is source 2?
1. Sorry, 2.
Right, it's R2. And then what do I do with R3? I update, right? Because I write to R3 again. D. Because by that point, I guarantee no one would need C, right? Because I already finished fetching and decoding every single instruction that needs C. I know that any future instruction would get that version of R3, right? So this is how renaming works. So let's say I finish the first instruction. This is what we do. When I finish, I say, hey, it's valid. Becomes 1, right? What is the value here?
3.
3, right? Obviously. So what is the next thing I should do?
Replace A with 3.
Replace any occurrence of A in the register file in this case that doesn't exist, so I don't have to update. And replace the entry of A in the reorder buffer with 3. Right? To be honest, most of the time when you are here and it's not valid, it's still A, right? Usually this is getting from the data forwarding. So usually if you can pick that up in the data forwarding, that is 3. Sometimes this can happen. Sometimes we already have that, right? So you say, hey, I have the letter, I have the value 3 already. So this become valid, it's finished. It finished the multiply as well because I took the value A from the data forwarding from the ALU. Then I finish. This becomes what? 3 plus 5, that's 8. Oh, 3 multiplied by 5, I'm sorry. I just screwed up the example. Yes, it did. I hate when I hit the erase everything. I guess you know the deal, but let me redo it again, right? So tag A, B, C, and D. So not valid. X, Y, C, and W. Source 1 is 1, 2, and then this is A, right? then you replace this with A, then source 2 is 5, right? And then for this, source 1 is 4, source 2 is 7. You replace R3 again from A into C, right? And then for the last one, you take C, and then source 2 is 2. Then you replace this with D. And when this becomes 1, you update, right? The value into 3, check who has A. This becomes updated, it goes into 3. Sometimes you get it from the data forward part. This can become 1 sooner because you take data forwarding, right? So once that's done, then you update anyone who has B with the value. So you can keep doing this. And this way, you rarely have to stop, right? Because you can keep going. You just think, hey, that's a tag. If you need it, go find it there, right? Well, so now we talk about reorder buffer. Let's talk about history buffer. It's kind of similar, but there's a quick difference. So history buffer, the idea is, well, the downside of reorder buffer is if exception happen, what do I do? Because, so let's go back here. If exception happen, what? Right? So what you do is you're gonna have to kind of retire this to actually update register file up on exception, right? You update the register file up on exception. You need to kind of finish whatever happened, right? So you have the true value of the register file, not just dangling tags. So if exception happen, let's say here, right? Register file is not updated, so you need to finish this, and finish this, and update everything in here. If exception happen in the middle of the execute or memory stage. So that's the downside of the reorder buffer. You don't have the fresh version that you can, when exception happen, throw it at the programmer right away, right? So that's what the history buffer comes into play. What if we can undo the updates to the version of the register file where exception occurs, right? So the history buffer would store the old value. It only gets updated when you finish the instruction. If there's an interrupt and exception, use this old value, throw it to the programmer right away. If the oldest instruction doesn't interrupt, then you discard the oldest destination register. So here's a key difference. In the reorder buffer, you update the register file whenever you have the value in the register file is going to be non-speculative. If you have the value, that's going to be the correct value, but it takes time to reach that correct value because it has to finish the write back. When the valid bit becomes 1, it means that instruction finished the write back, right? So that's what the reorder buffer is for. This can delay accessing new value from the register file. So when exception trigger, you need to make sure every single invalid bit in the register file get updated through the reorder buffer. History buffer is different. Register file will have the most updated version of the value. So you aggressively update the register file. Then you have another buffer that store the old value. So if exception happen, there you go. That's the version of the data that are old. Programmer, here you go. Check it out. So there's a trade-off here, right? Reorder buffer, you don't have the speculative value, you don't have the future value. History buffer, you have the future value, but you need to lock them. You need to maintain them, right? What if you want both of them? So this is the concept behind future file. So instead of having only one register file, our solution is simple. We have 2 versions. One of them is if exception happen, throw this. These are the version that happened after the write back. And then you have the future version of register file, which gets updated, right? Which gets updated when you finish the instruction in the reorder buffer. Reorder buffer still maintain the instruction. You haven't retired yet. You only commit the retired instruction into the architecture register file. Future file is maintained so that you can use it in the future. If future instruction need that in the pipeline, here you go, that's the data. Architectural register file is used for state recovery. For the interest of time, this is a little bit complicated, so we will do this next lecture because I kind of want to wrap things up, including the project proposal and review, right? But having two versions of the register file is costly. We can use indirection for that. We'll also talk about how we do this in the next lecture. So in this case, we have a future map that you use to speculate register value and use architectural map for state recovery. Because the goal here is exception happen, you need to recover. Non-exception happen, we want to be as aggressive. Go run as fast as possible if everything is not causing exception. So that's the deal, right? And then that is done through what we call register aliasing table. Again, we will talk about this in the example next lecture. So we'll do a recap of reorder buffer. We'll do a recap of history buffer, future file with register aliasing table, and then transition into out of order execution. How do we put everything together and look at modern CPU and here's what happened in the CPU you buy off the shelf nowadays, right? So that's next lecture. Before we end, I'll talk about the last thing, which should be pretty short and simple. It's called checkpointing. This concept of checkpointing is used everywhere in computer engineering and computer science. In the context of architecture, we also use it to restore the state. The key concept of checkpointing is, let's say you have a branch. An exception happened, right? Because what we've talked about so far, we haven't even talked about branching, control flow. What if exception happened in the if, but not in the else? Fun, right? Control flow trigger exception. How do we actually recover? So this is what we do to make sure we can recover. If we have branches, we keep a copy of future file. If we have a branch, we keep a copy of future file. This checkpoint, we call this checkpoint. This checkpoint copy are updated with an instruction whenever an instruction produces a register value. So why do we need this? We need it in case we mispredict the branch. Remember, branch prediction, right? We'll keep running. We'll keep putting things into the register file and future file, which means that if we mispredict, whatever is in the future file and whatever is in the register file is junk data because it's not something you're supposed to finish. So if we have misprediction, we restore. So because we have a copy of the future file, right? So we restore the version of the future file back when branch happened so we can recover. So that's checkpointing. Think of it this way. It's like playing games, right? And you save the game. Before you fight the boss, right? There are multiple things you can try when you fight a boss in a game. You can try option A, option B, option C. And you don't know which one is the best. Some option would lead you to losing the game. So you save it before you fight the boss. If you mispredict, which means you pick the wrong option, you load. Right? This is loading the game so that you can resume and fight the boss using the correct option. So that's what checkpointing is for. Is actually the reason why I talk about this first, because we cover future file already. We haven't go through the example, but you have the concept of future files, whatever is in the future. it's in the pipeline. It hasn't finished. So if you want to recover, keep a copy of that. When you happen to have branch misprediction, recover that copy. All right. So let me kind of wrap up today's lecture because there's a lot of new material that can be super confusing. I'm going to combine the future file, register, aliasing table, and out of order execution into the next lecture. It's going to be 3 hours, likely 2 hours with a bunch of examples to make things clear, right? Because that's a wrap for most of the processor design. We'll have one more lecture, and then we have the next lecture, out of order processor. The lecture after that is load store, dealing with what do we do with the memory stage, and then we have the exam. Before we leave today, Muhammad, you did the review. Opada, we still have the deadline opening, so you can submit tonight if you want. This week paper is about, I think, branch prediction, right? Yeah, Muhammad, I already grade your review is good. Please keep that up. And I didn't put a comment because since you submit earlier, I can give you the feedback right here. But that's a good review. I appreciate that you put in your own opinion more compared to earlier reviews. That's awesome. That's actually what I'm looking for, right? I want to see what you think. I want to focus on a technical point of view of each of the paper. And now you might have realized that with newer paper that you see like anything above 2000, it's much easier to read the writing. Sometimes you need a background. That's okay. That's what the class is for. You are actually learning the background, but the style would be more familiar, right? So that you can focus on the technical aspect, right? Project proposal. I have a brief submission on Canvas. I explain what I want with the proposal, which is basically let me know what you want to work on. What's the goal? Why should anyone care? Is that important? And what's your plan? Because I want to see the plan. I want to know how you're gonna reach the deadline on time and have a full project. For OPAD, you emailed me already last week about your plan. So everything. So just submit that PDF of the slides. Muhammad, if you want to get my feedback, feel free to email me about your project, potential project, brief description. Otherwise, please make sure you submit this so I know what you're trying to work on. Right? It's just a timestamp thing. Make sure you have that submitted so I know is it too easy or too hard so I can give you feedback. If you talk to me earlier through email, I will have already given you the feedback, so that's okay as well. Right? So that's your option. You can get my feedback earlier. You can wait until the deadline and you submit. I'm giving the feedback as soon as possible afterward, but then it means that you're gonna start your project a little bit later. You can use the time for lab 2 as well. Lab 2 is not simple, right? So you can use the time either for your project proposal or lab 2. It's not simple, but it's not that hard, right? Once you know what you have to do, it's not that hard. Just make sure you have now, instead of one state, the next state update, right, from lab 1. Then you have each state for each pipeline stages. Stage for fetch, state for decode, state for memory, state for execute, and state for write back, and that basically is my next state, right? And then for each of the state, you have updating things based on the instruction of the state. That's all. That's how you do pipelining. For data forwarding, just aggressively look for, okay, for the future state, if I need the data, is that in the execute? Is that in the memory? Or is that in the write back? If it is, forward that data to me rather than getting it from the register file, and that's all. Feel free to discuss your project proposal with me. If you have already done so, awesome. Please just submit your slides there in the PDF form. It's good enough, and thanks for that. If you haven't checked with me, feel free to check with me, right? I can give you feedback on whether that's too hard or too easy, because sometimes your project is too grand, so we need to make sure we cut it off. So for the class, sometimes it's too obvious, right? if it's too obvious, like, hey, you need to make this harder. Like this is like an undergraduate second year project. I don't accept that. So we need to kind of like make that balance, right? One last thing, midterm notice. It's coming up on September 30th, which is so the next class we'll talk about out of order execution. The class afterward we will talk about the load store handling in the memory before we transition full blown into anything outside of the CPU, the cache, the DRAM, multi-threading and things like that, right? So we'll do a midterm. Make sure you know the basic material. Make sure you can go through the example I went over. I will give you a sample exam from last year so that you can take a look at that. But there's a difference, right? Because of COVID, we don't have everything live. So previous year exam is 3 hours. I will aim so that you can finish in 3 hours. But I'm going to give you 24 hours for that. It's open book because I have no way to control what you're going to do, right? So open book, open internet. Good luck finding the answer because I'm going to make sure you cannot find the answer. Like there's no obvious answer. You have to think, right? But it should not be too hard. I'm gonna make sure that you can finish this in 3 hours because it's not fair. So I've seen some of the people who once things become online, it's like, hey, let's do a 24-hour exam. And it's not fair for me to expect you that you're gonna use all 24 hours for that. I want to make sure it's 3 hours exam worth of how hard it is. And then you have a time for you to pick what do you want to do. I mean, to be honest, I even think about like I can make it 48 hours. Do you want 48 hours? It's gonna be the same length anyway. Okay,
No.
I was like, no, I don't trust you. Okay, so yeah, so then let's do 24 hours. Then you usually I'll make sure just like it's good enough. You can pick the 3 hour. Usually it's a 3 hour in class, so you can ask me questions from the exam. Then you might need like 1 or 2 more hours to finish up, if you want. But again, if you know everything perfectly, it should be finishable in like 1.5 hours or 2 hours. And that's it for today. We finished a little bit earlier, so now I want to open up the floor for both of you. Like, if you have any questions about the material we covered today, or if you have any questions about the lab or the project.
Yes, I do have a few questions about lab 2. So
Yeah, sure.
okay.
Let me have let me use this blank slide.
Okay, so I actually started drawing sketch of lab 2. So in lab 1 we just used a switch. I just used switch statement to make cases of each of the instruction, like when there is a branch instruction or add or add IO. And what the basic sketch is, it perform all the operations like in a single cycle.
Yeah.
It isn't divided into fetch, decode, execute, memory, and write back. So lab 2 is basically says that it is based on lab 1, and we will have to basically divide that into sections now.
Yes.
So I was making sketch, but can you just give me a startup like how to do
Sure,
that
sure,
lab
sure.
2?
Yes.
Because I
Yeah,
tried, but
we'll do for sure. So I'm gonna draw a parallel between lab 1 and lab 2, right? Lab 1, the main task is, hey, what's my next state? So that when I cycle and call the function called process instruction, I update the current state with next state. This is single cycle, right? One cycle, everything is done. In lab 2, because it's pipelining, at the end, this is the next state, right? Which is basically whatever write back supposed to do, right? Write back. You have memory, you have execute, you have decode, and you have the fetch, right? And somehow you have to kind of fetch the correct thing, which is basically PC+4, right? So this is what you do. You will then add the state, right? This is going to be something called, for example, state after memory. This is like, if you need something that happened after the main memory, after the memory state happened, go look at here. What's in there will be obviously the PC of that instruction, the register file for that instruction, right? Because you have all the value in there. This will be state. Execute, which again will have its own version of PC because it's different instruction and a different set of register. Do the same thing for state. Decode. Right. Over here, again, you have PC. You have register. And again, over here, state. Fetch, right? Again, PC and the register that tie with the state where you're gonna update in the execute. What else? If you just maintain this, it won't be enough, right? Because, for example, in the decode, right, you have things like what's my immediate, what's RS, what's RT, right? So maintain that as well inside each of the state. Maintain what's RS, what's RT, so that when you proceed to the pipeline, this is what happens. I'm going to use a different color ink, right? So when you clock, right, basically next state get updated. So this is current state, right? So this obviously get updated. State memory becomes the next state. State execute become memory. Decode become execute, fetch become decode, and you have a new state for the fetch. So when you clock it, now you have intermediate temporary state for each instruction in your pipeline. And this way, you're gonna be able to easily maintain the state in your pipeline, then easily transition all the things in the middle, like, okay, what is this instruction? What's the immediate? What's the register for the source? What's the destination? Where do I get the operand? So you can pass it out through the pipeline. Then when you have to do stalling, like when there's a data dependency in the decode, you then check, right? You check, okay, who generate my operand? If there's someone generating operand, you maintain decode doesn't move to execute, decode stay there, fetch stay there, and then execute move to memory move to write back finish. Keep doing that until the condition check becomes true. Basically means no one modified the register operand. I have the most updated version of the data and we resume the pipeline. So that's version 1 with stalling. With data forwarding, then you have another check say, hey, who owns the most updated version of the data? If that is in the execute stage, give me that. If it's in the memory stage, give me that. So basically that's what you can do, right? So this is probably the easiest way to do this. There are more optimization you can do. For example, you don't have to always maintain a version of the register file. You just have to maintain the ID and the value you're updating, right? So you can optimize the space requirement for your own simulator, saying, hey, for each of the state, I just need the ID and need the value. I don't need every single entry. So that's one thing you can do, right? So then from here, this is good enough for sure. And then you can optimize this if you have time or you want. If you're busy, just like, okay, every state has its own copy of rec file. In reality, that doesn't exist, right? In reality, it should be just one value. Just be aware of that. But for the sake of writing simulator, simulator is just what imitate the pipeline, right? So as long as you can imitate it correctly, it's fine.
And I actually do have a question about the project also.
Sure.
I was thinking of we actually in image processing we always need to process images in parallel to actually some in applications like high speed, something moving in a high speed, so we will have to achieve a desired frame rate at the output, so we will have to do parallel processing in order to achieve that FPS. So Is this can be a good project to take a video stream or images from the camera and then process it in parallel?
Yeah,
Because
that's a perfectly fine project. To be honest, it's like kind of similar to what Opad is doing, but it's for his algorithm. For yours, it's gonna be your algorithm, and you will do it in parallel. So that's perfectly fine. So there are a couple of things that I would suggest you to do. First of all, Amdahl's law, right? Figure out which part can be done in parallel, which part is your bottleneck. Obviously, that would help, right? So that you aim for the right places. There are performance profiler tools that you can apply depending on how you run it, right? You profile how long does it take to do each of the function call. You then look at the algorithm. Is it friendly for parallel programming or is it not friendly? If it's not friendly, are there friendly algorithms? Because 100%, I think that's a parallel version of whatever you want to do. Then you parallelize the code and the algorithm and see, hey, how much speed up do you get? Right? Can you do better? How fast can it be? So that's a perfectly fine project. Just feel free to put things together and point it out to me. It's like, what application are you trying to speeding up? What do you expect to learn? And for both of your projects, right, feel free to for the 150% goal, for example, you want to utilize the GPU, that's a perfectly fine way to kind of like reach for the store. It's like, hey, I now implement whatever I have in GPU and it's even faster. Because I believe for both of your applications, it might be beneficial to use the GPU. But for a simpler task, like maybe start with OpenMP, which is a library for you to utilize parallel execution of code, especially things in a loop. Okay, so go learn that. It shouldn't be too hard. It actually not hard at all. And see how fast can it get. And also do a breakdown like, okay, I run my whole like pipeline of the program and this is where things get slow. I mean software pipeline, right? Each of the process would contribute to a different amount of total execution time and see what can be made faster. So that's totally okay. That's actually great project.
all right. So I will document this and I will then submit that in Canvas and I will
Yeah,
also
but don't
email.
have to make you don't have to make it too formal. Just put it in something that I can understand. Like treat me as human who can read English. So as long as I know what you're trying to do, perfect, right?
All right.
Yeah, minimize the time and maximize like the key message that you want to tell me. I'd rather have you spend more time on the lab. So,
All right.
all right. So anything else you want to ask? All right, so if there's nothing else, again, before we leave today, we will do a recap of the future file with register listing table and out of order execution next week. I think 3 hours. We probably should be done within like 1.5 hours or 2 hours. And then if we have time for 1 hour, I would actually continue on to the like what to do with load and store. If not, I'm gonna do a quick recap of like what we've been covered so far, and then kind of wrap it up with the week after with like dealing with load and store and do a review of what we covered so far for the midterm. All right. If that's all, then I think that's it for the class. Thank you so much for attending, and have a good the rest of the week. And if you have anything, let me know. All right.
All right. Thank you.
Okay, cool. Take care all, and I'll see you both next week on Thursday.